Hello students, welcome back. Let us continue our discussion of the thermodynamics of electrochemical cells. So, we have discussed two problems in the last class, and so in today's class I am going to talk about a third problem. And this third problem is again a very simple one. You are required to estimate the standard cell potential at 298 Kelvin of this cell, which we have represented to you over here. So, obviously, the starting point is the half cell reaction. But before I do that, let me try and explain to you once again what I have over here. Here I have on the left hand side a platinum wire on which the hydrogen gas is bubbled, and this platinum wire is in contact with an aqueous solution of HBr. And in that same solution, I have a silver wire dipped over which there is a silver bromide layer, which is a solid layer. So, the silver wire and the platinum wire are then connected to the external circuit, and we are going to look at the standard cell potential of this cell at 298 Kelvin. So, as I said, let us start by writing down the half cell reaction. So, the first one is how silver bromide solid takes up a single electron, giving rise to silver solid and releases bromide ion in the aqueous medium. And here I have also written down the standard reduction potential for this couple silver bromide and silver solid, okay, and the value is plus 0.07 volt. I can again write down the other reduction reaction that I should be worried about, whereby the reduction reaction that I write is H plus ion aqueous takes up one electron, giving rise to half hydrogen gas. So, you might be wondering how I can write half molecule of hydrogen gas. Actually, what we are writing down are applicable for the moles. Therefore, this half cell reaction would correspond to 1 mole of H plus ion in aqueous solution will take up 1 mole of electron, giving rise to half mole of hydrogen gas. Okay. Now, since mole is a very large number, therefore, there are still a very large number of hydrogen molecules in half mole of hydrogen gas. So, I tabulate here the E naught value for this couple, which is by under standard condition is 0 volt if I am maintaining the hydrogen gas over here at 1 bar and I am using unit activity of the HBr aqueous solution. So, now I will use the notation that reduction at cathode and reduction on the right, and oxidation at anode and oxidation on left, and to write down the net cell reaction, therefore, I will subtract the second equation from the first one. So, let me explicitly write down the algebraic equation that you will get by subtracting the second one from the first. So, you are going to get AgBr solid minus H plus aqueous, giving rise to silver solid plus bromide ion in aqueous medium minus half hydrogen gas. Now, this is not how we write down chemical reactions. So, I will rearrange this algebraic equation to get the net cell reaction, which is silver bromide solid reacting with hydrogen gas gives rise to silver solid, H plus in aqueous medium and Br minus in aqueous medium. So, this is the net cell reaction for this particular cell. Now, moving ahead, I should be able to write down the standard cell potential E naught as E naught R minus E naught L, because I am taking the standard reduction potential and the silver bromide silver solid, these two redox couple, they have a higher standard reduction potential, thereby telling us that they can be placed at the cathode and the hydrogen gas electrode can be placed at the anode for a spontaneous transfer of flow of current in the external circuit, and there the standard cell potential will turn out to be, obviously here this is going to be 0.07 volt. Now, let me just recount for you. So, as discussed before, we can also predict the equilibrium constant, and here K equilibrium would be given by exponential of NF E naught cell divided by RT. We can calculate E naught cell, which we have shown to be equal to plus 0.07 volt. N in this case is equal to 1, and knowing the Coulomb constant and the universal gas constant, and since we are working at a temperature of 298 Kelvin, I can find out K equilibrium. And you will always also be able to write down the equilibrium constant in terms of the activities of H plus ion in the aqueous medium multiplied by activity of bromide ion in the aqueous medium. Okay. Now, from here we go to another problem which uses the same cell, but in this particular case we have measured the standard cell potential over a range of temperatures, and in the experiment the result, the measured value of standard cell potential has been fitted to an equation. It is given as E naught in volt, that is given by 0.01 minus 10 to the power of 4 into T minus 298 minus this small term into T minus 298 whole squared. Now, given this experimental data, your task is to estimate the standard reaction entropy and standard reaction enthalpy for the electrochemical reaction that takes place in this cell. So, here the set of information provided to you is a little bit different. You have been provided the standard cell potential measured over a range of temperatures. So, E naught is provided to you as a function of temperature, and I want you to find out, let us say, to start with, the standard reaction entropy. Now, we know from our earlier discussion that the standard reaction entropy for the electrochemical reaction is given by NF into a temperature derivative of the standard cell potential under constant pressure. Therefore, the requirement of the required input for the calculation of the standard reaction entropy is that I know first the number of electrons transferred in the net cell reaction, second the Faraday constant, which we know that it is 96,500 Coulomb per mole, and finally the temperature derivative of E naught or the cell potential. In this case it would be del E naught del T. In order to solve this problem, therefore, the first step would be, do I know the number of electrons transferred for the net cell reaction? So, for that purpose, once again I will write down the half cell reactions. So, this is the reduction reaction for the redox couple silver bromide solid, silver solid, and this is the half cell reaction for the redox couple H plus and a hydrogen gas. Now, I am going to once again follow the convention that there is reduction on right and cathode on right, and oxidation on left, that is anode on left. But here, as I have written the reaction in terms of a reduction, therefore, to obtain the net cell reaction, I will have to just subtract. Okay. So, when I subtract and write down the net cell reaction, I understand that in the balanced chemical reaction as written over here, how many electrons are involved? There is only 1 mole of electron involved per mole of conversion of solid silver bromide in reaction with half mole of hydrogen gas, producing 1 mole of silver solid and 1 mole each of H plus aqueous and Br minus. Now, what is the second step? The second step is you need to know del E naught del T at constant pressure. Now, it is given to you that E naught is a function of temperature, and I have obtained this information from the experimental data. So, I can very quickly find out what del E naught del T P would be as from this given relationship. So, obviously, the first term, this is a constant independent of temperature. So, that will not appear in your expression for the derivative. The next term is dependent on temperature. It has a constant prefactor, negative sign, a constant prefactor, then T minus 298. So, if I take a temperature derivative of this term, I will be left with minus 1 into 10 to the power of minus 4, and the result of derivative of this term is be equal to 1. Now, if I look into the second term, that is minus 2 into 10 to the power of minus 6 multiplied by this T minus 298 whole square. So, when I take a temperature derivative of this term, what I am left with is this 2 comes down from here. So, it is 4 into 10 to the power of minus 6 into T minus 298, simple derivative. So, that means that I can write down that this is 1 into minus 1 into 10 to the power of minus 4. This would be the value at 298 Kelvin, and you must realize that the unit of this ratio that I am talking about, not ratio, derivative that I am talking about, must be volt per Kelvin. That is because I have expressed here E naught in volt and temperature in Kelvin. Therefore, del E naught del T P has a unit of volt per Kelvin. Now, moving ahead, now I know that I am going to evaluate delta S naught, which is a product of N F del E naught del T P. I know the value of N, I know the value of temperature derivative of E naught at constant pressure at 298 Kelvin, and therefore, I can calculate delta S naught. So, what is delta S naught? That would be 1 into 96,500 coulomb per mole multiplied by the third quantity is this, whose value is this quantity, that is minus 1 into 10 to the power of minus 4 volt per Kelvin. So, once I do that, this is a very simple calculation, and you should be able to say that minus 9 delta S naught is equal to minus 9.65 coulomb volt Kelvin inverse mole inverse. But there is some more simplification that is possible over here, and can you tell me what that is? I look back and see that my question requires me to report the value of standard reaction entropy in joules per Kelvin per mole. And what is it that I have got over here? I have got coulomb, volt, Kelvin inverse, mole inverse. Do I know the relationship between 1 joule and 1 coulomb volt? Actually, they are equal. Therefore, I can immediately write down that delta S naught is equal to minus 9.65 joule per Kelvin inverse per mole. Now, moving ahead, this is not the end of the exercise. The question wants me to find out the standard reaction enthalpy in units of kilojoules per mole at 298 Kelvin. So, to evaluate delta H naught, I will just try to recall that the standard reaction Gibbs free energy is equal to minus NF E naught for this electrochemical cell, and I also know that delta G naught is equal to delta H naught minus T into delta S naught, and therefore, by knowing E naught as a function of temperature and knowing delta S naught, which involves del T of E naught at constant pressure, I should be able to find out delta H naught. So, what is delta H naught? That is delta G naught plus T into delta S naught. So, if I write it down, then I will replace delta G naught by minus NF E naught, and then I will go ahead incorporate the expression for delta S naught that I have already used, and this is going to be my final expression for the standard reaction enthalpy, which is going to be my working formula. So, moving ahead, to find out delta H naught, I require this quantity as well as this quantity at 298 Kelvin. So, do I know what these values are? Now, E naught is given to be a value like this in the units of volt. So, at 298 Kelvin, I understand that the second term vanishes and the third term also vanishes. Therefore, I will say that for the given cell, E naught is equal to 0.01 volt. And I also have shown you that del E naught del T P, that is equal to minus 1 into 10 to the power of minus 4 volt per Kelvin. So, I will go ahead and I will evaluate delta H naught. I will evaluate delta H naught as 1 into 96,500 coulomb per mole, representing the contribution of the first two terms here, and then I will have this temperature into the temperature derivative of the standard cell potential minus the value of E naught that I have got at 298 Kelvin. So, once that is done, then delta H naught turns out to be minus 3.84 kilojoules per mole. Now, moving ahead, therefore, what we have found out is the measurement was done by preparing the electrochemical cell and then maintaining it at different temperatures. Then at every temperature, the standard cell potential was measured. So, once that was measured, then a fitting equation was used to describe the temperature dependence of E naught, and this is the equation that has been given to you. Now, when you know this, then you were asked to find out the standard reaction entropy and the standard reaction enthalpy at a given temperature. So, if that is so, all you can do is you find out the derivative of temperature of this particular derivative with respect to temperature of this quantity E naught, use that to find out the standard reaction entropy and also find out the standard reaction enthalpy. And we find that here this is going to be an exothermic electrochemical reaction. So, in this lecture, what I have done is I have given you a brief overview of how to extract important thermodynamic quantities related to an electrochemical reaction. In this way, the cell that I have built over here by coupling the silver bromide silver electrode with a standard hydrogen electrode, I could show that it would spontaneously undergo the cell reaction that we derived. Why is that so? That is because we found that under standard condition E naught was at 298 Kelvin was positive, therefore, delta G naught was negative, and under those conditions we could find out the associated change in standard reaction entropy and standard reaction enthalpy. That is all for this particular lecture, and I will see you in the next lecture again. Thank you.